Alright, so this is going to be a video to help you with understand the logic gates and what's happening with the electronics in EE223 Digital and Analog Electronics 1, because it can be a bit confusing when you've never worked with this stuff before and should just go with whatever these symbols are and trust whatever these gates are in these black circuit well, integrated chips are doing. So I'm going to start off with very basics just so you understand the equivalent in Minecraft. So here is just standard wiring. We have a lever here. This is going to be our input and can be on or off, 0 or 1. I'm going to use a light beside it to show you more visibly if it's on or off. Then I will also have a light at the other end, redstone lamps, these are called, and that's going to be our output. Off is 0, on is 1. And then there will be a sign showing the truth table or some form of it. For like the 0 input, the output will be 0. The 1 input, the output will be 1. And this is redstone dust. This will be used for connecting one point to another, or electricity from one point to another. So you don't need 5 volts in ground. It's just kind of like I turn this lever on, and it will send power to this redstone lamp, and I don't need anything to bring power back. It's just direct power. So yeah, that's simple wiring. Turn the thing on, and the thing turns on. Turn the thing off, and the thing turns off. Great. Next up is a NOT gate or an inverter. So in Minecraft, that is done by these things here called redstone torches. They naturally are on, and when you can place them on the top of blocks or on the side of blocks. You can't place them underneath, and when they're powered, so if the block that they're on is powered, then they will turn off. So that inverts the signal that they're sending out. So for example here, if I turn on this lever, it'll power this block, which will power this redstone torch, which will depower this redstone, turning off the lamp. Just like that. I do it from here so you can see the redstone torch turning off. Yeah, and the redstone torch is on. So next up is an OR gate. So this is done by having either, so have a look at the truth table here. So the truth table, when the input is 0, the output is 1. When the input is 1, the output is 0. Inverted. I won't be going through the truth table for all of them. It's just the first few so you understand for when you're looking through this world yourself if you want later. So and then we have an OR gate. So here we have 2 levers, and if I turn on this lever, then that's going to power this block, which powers the redstone dust here, which powers the lamp. I don't need to do anything with this block because I just need one source of power to turn on the redstone. I can turn it on still and nothing changes, but when I turn this one off, now this one is the only one powering this redstone, and that's keeping the light on. The light only turns off when both are off, just like that. Yeah, so the truth table here, because I have 2 inputs, it's 0, 0, and output is 0, and then 0, 1, the output is 1, 1, 0, the output is 1, and 1, 1, the output is 1. Alright, so next up is a NOR gate. The N stands for NOT, so we have a NOT OR gate, or an inverted OR gate. So that is simply an OR gate, as you can see here, but we have an inverted output. So that's just done by putting a redstone torch on the output. I have a different colored concrete here. That is to show you the different stages, splitting everything up. So we have stage 1 or step 1 or part 1, whatever you want to call it. That's just the OR gate. And then part 2 is just connecting the torch to the redstone dust and then to the lamp. I don't even need this. I'm just I can just have the lamp directly beside the torch and it'll work. I'm just showing you this because it's easier for you to understand if you don't fully understand redstone and this is your first time. If you already understand redstone, you might want to skip to some of the later parts or just have a look at the world yourself. There are other ways you can do these layouts, by the way, and like this can be compacted quite a bit to just being a single redstone lamp, 2 levers, and a torch on the other side of the block. But this is for demonstration purposes. It's laid out flat and a bit larger, so it's easier to understand and see what's going on. So then you can try and make your own, or try modify it to fit whatever goal you want, or play around and test. So next we have an AND gate. So here we have 2 levers with inverted inputs, and then we have an OR gate. That's one way you can describe an AND gate. It is just the light will turn on, the output will turn on only when both inputs are on. So right now, this torch here is off because both redstone torches here are on, because both levers are off. So if I turn one of the levers on, that only turns one of the torches off. I need both torches off to turn off this wire, allowing this redstone torch to turn on, powering the output. And then if I turn one of the levers off again, that turns a redstone torch back on, and turns off the output. Very simple. So the next up is a NAND gate, and not AND gate, an inverted AND gate. These are you only need NAND gates technically to build a PC, because everything else can be made using NAND gates. Like a NOT gate can be made by just connecting both inputs to the one wire, for example. So to invert the output, you would put a redstone torch at the other end, but then of course you have you have 2 NOTs that cancels each other out. So we just remove the torch. You can have the torch if you want, but I just showed you here to show you like another way to describe it. It's basically just an OR gate with inverted inputs. So here right now both levers are off and both torches then are on. If I turn one of the levers on, the torch turns off and the power stays on because the other torch is still on. I need both levers on to turn the output off. That's inverted AND gate. And there you go. So I'll show you now actually. I can invert the so there's an AND gate there, and then I invert the output. It's the exact same thing. It's just a bit larger and a bit slower. So I need both levers on to turn the output off. And if any of the levers are off, then the output's on. So it's the same thing. I just removed the torches because it's more compact, and it's to show you that 2 inverts cancel each other out. Next up is an XOR. So this is exclusive OR. So it's only on when you have odd inputs, or when either of them is on, not both. So when both are the same, the output is off. So for example, right now, both are off, so the output is off. That's pretty normal. I turn one of the inputs on, and the output is on. I turn both of the inputs on, and the output turns off. I then go back to one input, and it puts on. So how this works, let's start off with one aside. So I have the signal inverted, then it's inverted again. That's the same as just having it directly powered, because they both cancel out. So that's why when I turn this on, the output's on. And same with the other side, it's just 2 inverters. But then I have an AND gate. That's what the red is. So you have the AND gate, and that means when both are on, it will go and so this here is a NOR gate. So the output now will turn off these NOR gates, which is why the output is off when both inputs are on. That's how it's described. So red is the AND gate, orange is like NOR gate for the sides, and yellow is the NOR gate for the AND, and then you have your output wire to this. So that's how an XOR can work. Next up is XNOR. It's exclusive NOR gate, or exclusive not OR. So this is on. So this is just an XOR gate with an inverted output, just like how an NAND gate is an AND gate with an inverted output, and an OR gate, a NOR gate is an OR gate with inverted output, and XNOR gate is an XOR gate with inverted output. So when both are the same or matching, both inputs are matching, the output is on. When they are odd, or one is on and the other is off, the output is off. When they're both the same, the output is on. And then going back to odd, the output is off. And that is just an XOR gate, as you can see here, but the output is inverted. There is a torch here, there's no torch there. Same thing otherwise. You have your AND gate, you have your two inversions, your NOR gate. Yeah, same thing. Okay, so next up is a half adder. This is an XOR gate and an AND gate. So that is because you want 0 plus 0 here, for example. That gives you 0. 0 plus 1. Sorry, 0 plus 0 is 0 carry 0. 0 plus 1 is 1 carry 0. 1 plus 1, that gives you 2, but you don't have 2 in binary, so that is, so you carry over the 1, so that's where the carry turns on, and the units is 0, so that is 0 carry 1, and then 1 plus 0, that is 1 carry 0, and that's it. So that, as I said, is an XOR gate and an AND gate, but as I mentioned earlier, an XOR gate already has an AND gate built into it, or at least this design does. So you can just piggyback off that, which is what I'm doing, and taking the output of that AND gate for the carry bit. And you could also build a separate AND gate if you really wanted, but yeah, sometimes you already have an AND gate inbuilt, or some. Yeah, so that's one of the advantages of playing around with the actual internals of it. You can see how it actually works, and that is what this is for. A bit more tangible. So now we have an OS NOR latch, reset set latch. This is used for memory. So here we have our output. If I push this button, then the output is on. I've set it to on. No matter what I do with this button now, it will stay on. It will only turn off when I push the reset button. So that is done by having two inverters feeding into each other. Technically, it'd be NOR gates feeding into each other. So if I then power this block here, this turns off this torch, and that allows this torch to turn on, which will keep this torch off because it's powering the same block or the same input. And then if I can only reset it by pushing this button, because that powers this block, which turns off the torch, allowing the torch it was turning off to turn on, and that keeps it there locked. That's how memory works. You would have a bunch of other logic gates to figure out the address, to pick which NOR latch to access, and then just set it. So next up is monostable circuit. So this here is a rising edge monostable circuit. So in Minecraft, Redstone has a certain each Redstone torch. So in Minecraft, Redstone updates 10 times a second. These are called ticks. There are 10 Redstone ticks in a second. So a Redstone torch takes 1 tick to update. So this is how you can time stuff. So when I turn on this lever, that's going to take 1 tick to turn off this Redstone torch. So then after 2 ticks, or a total of 2 ticks, this Redstone torch would turn on. Okay, because of just the fact that this line will be off, so this Redstone torch would turn on because it's 2 inverters. Okay, but then following this path here, the orange path, the second path, I turn on the lever, this turns the Redstone torch off, after 2 ticks then, this redstone torch turns on. So after 3 ticks, it turns this redstone torch back off. And that gives us a pulse. As you can see here, if I turn the lever on, this redstone lamp stays on constantly, but that one there, you may not have seen it because of the coordinates in the way. That lamp pulses on for a brief moment, and only happens when I turn the lever on. So I turn the lever on, it pulses. I turn the lever off, it does not pulse. That is why it's rising edge, because it's only when the signal turns on, or the signal goes high, or 1. This is the same thing, but a bit more compact. This here is a redstone repeater. So how a redstone repeater works, or I should, as you can see, so our redstone repeater is 2 redstone torches with some redstone in the middle. So that is representative of this here. We have 2 redstone torches that inverts the signal twice. So it's just simple powering with, say, 2 inverters, so they cancel, and it's directly powering. This is because in Minecraft, redstone can only power things up to 15 blocks away. So as you can see here, this lamp turns on, this lamp does not, because it's too far away. So this is how you would increase the signal, or boost the signal. You would use 2 redstone torches. This got shortened down to a repeater, and you can also change the delay on the repeater. So this here is 1 tick, 2 ticks delay, 3 ticks delay, 4 ticks delay. So that's useful for timing stuff, or extending a signal. So that so that's what the repeater does. So here it's just the same thing, but except we have compacted it by using a repeater, and we set it to 3 ticks delay. So if I turn this lever on, just like that, the redstone lamp turns on for a short pulse. So next up is falling edge monostable circuits. So that is done. That can be done by just inverting the input. So now when I'm going high, it's now going low. So when I turn this lever on, nothing happens. When I turn the lever off, it pulses. So that is, as I said earlier, is done by inverting the input. That would be done by adding a torch before these 2 torches. Of course, 2 torches cancel out. So, or 2 inversions cancel out. So I just got rid of it. And so now we have direct power to this torch here, the output torch there. And then we have the inverted torch, that's that torch there, going to here, and then the pulse. Same thing with a redstone repeater. Of course, since the redstone repeater already has 2 torches built into it, we can't actually compact it like that. We have to invert the input like we technically are doing. So that is why there's a torch there, and then this torch here is that torch there, the repeater, and then the output torch there. So when I turn the lever on, nothing happens. Turn the lever off, we get a pulse. So next up is the JK flip-flop. So here we have our clock. If I turn on the clock when J and K are off, nothing happens. So also our outputs here are Q and Q bar, set, reset, 1, 0, whatever you want to call it. So if I turn J on, when I hit the clock, of course Q is going to turn on and Q bar is going to turn off. And it's going to stay like that. And then if I turn K on and J off, it's going to switch to Q bar to being on, no matter what I do with the clock. And then when I turn both on, it's going to swap each time. Q and Q bar, they just swap each time. So what this is we have the clock is a monostable circuit. So we have an AND gate here. This is a 3-input AND gate. It's just like that, except I've extended it a bit and added another torch. So now all 3 torches have to be off for this redstone torch here on the output to turn on, meaning all three inputs have to be on for this redstone torch to be on. So that's the three input AND gate. One of them is the J, one of them is the clock, or the monostable circuit, whatever way you want to look at it. And then the other is like feedback of the state of the latch, because this here is an OS NOR latch. As you can see, it's just like it is over here with the two buttons. Just sideways and the yellow now. We have some feedback part here, that's green. And yeah, that's about it. So when we so this, of course, monostable circuit, it will turn on here. Actually, we'll go to this side because this side's on. So it'll pulse, and that will turn this redstone torch off. That means all of this redstone here is off, turning on this redstone torch, latching it, and that means that this redstone here will turn off, allowing this redstone torch to turn on, and that will turn off this torch, allowing this side here to toggle. Meanwhile, this side here will turn on, and this torch will turn off, so this torch disables this AND gate. And that's how it works. If we then go here, I have a 3-wide flip-flop. So these here are all flat. The designs here are flattened out and opened up a bit so that they're easy to follow and see. This is me redesigning it so it's a bit more compact for my use, where it's just easy to be 3-wide and the inputs are a bit easier to work with for what I was doing. So for this for a design over there. So here we still have the same thing of J, K, Q, Q bar. So if we clock, nothing happens because neither J or K are on. We turn on J and we clock it. As you can see, Q turns on. We turn on K and Q bar turns on and Q turns off. And then we turn them both on and it toggles. So a toggle is when it toggles like this. If you have J and K both on or both high, it's sometimes called a flip-flop. So in this configuration, it's called a flip-flop. Yeah. So next up is just a simple clock. So this is what would actually be the clock for there. This one's relatively slow. It's just so you can see it visually. Of course, these clocks can be much faster. I can adjust the timings here by changing the repeaters. So as you can see, it's gotten a bit faster. I can slow it down. Yeah. So that this is a redstone conventional old school redstone clock in Minecraft. There's other ways to do this, like for example, OS NOR latches. They actually only require you can use more torches. You only need an even number of torches because of how it works. If you use an odd number, you will also get a clock. So that's a cool fact about those are really old torches before, say old clocks before repeaters existed. Redstone torch clocks. There's more modern ways to do this, but I'm showing you everything with standard redstone components because it's easier to work with, to understand here. If you're actually building in Minecraft redstone contraptions, you may use other components such as pistons, droppers, comparators, and everything else, and they can give you more compact methods to do these sometimes, or louder methods sometimes if you're using pistons, or just fit in places that you can't use conventional redstone. So this clock is used, as I said earlier, for clocking stuff like your JK flip-flops. Let's turn this clock off. So now we have a synchronous 4-bit counter. So yeah, we have our clock here, and it's counting up in binary. As you can see here, we have 1s there, 2s here, 4's here and 8's there. So it's counting every binary. So the units or the 1s should toggle every single time. 2's every time the 1's turns off. 4's every time the 2's turns off. And yeah, so 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, and 1, 1, 0. Yeah, you see how it goes. So how that works, we have a clock here controlling everything. And then, so we then have our, that's why I was showing you this 3-wide design here. I just moved it, copied it 4 times here. So we have one JK flip-flop here, feeding into another JK flip-flop here, into another JK flip-flop here, into another here. And then we're taking our Q output as the left side here. That's going into those 4 outputs there. So our clock goes into a monostable circuit first, just so it's a pulse, and then that goes on to our outputs, and then here we have an option for counting up or down. So right now it's counting up, and all this is doing is it's taking our Q or Q bar output and it's ANDing it with this wire or that wire. So if we want to count up, we will use this side of everything, and that will mean that it'll toggle whenever Q is high, or if we want to count down, it'll toggle whenever Q bar is high. So I'll show you that now. Actually, I'll do that later, just because we can go on to here. This is, of course, a multiplexer. You have a 4-bit input here. You have a 7-bit output. Bunch of AND gates, NAND gates, OR gates, NOR gates. And then you have a counter. 3, 4, this is segment, 7 segment, 5, 6, 7, 8, 9, 10, A, B, then hexadecimal, C, D, E, F, and loop back to 0. Lovely. So that's that. You can try and look at that if you want. I've labeled all of the segments. You can have a look at the actual logic if you want in there yourself. Okay, so yeah, counting up is if this side is high, counting down is if this side is high. So then if for example, if I flip this, it just switches this wire to be the one used, and that just changes the order it's counting in. As you can see, C, B, A, 9, 8, yeah, 7. And then you have, if you actually remember though, we have Q and Q bar, so you could also take an output from here on this other side. So if you are counting up, of course Q is counting up, Q bar though is counting down. And then if you swap it, Q bar is counting up, Q is counting down. So that's something you aren't really taught in this module, but if you were able to play around with stuff, for example, you could see that and figure it out. And that's kind of the advantage. You can just mess around here and figure out how stuff works. Hope you get a better understanding with all this stuff, because it can be kind of difficult if you haven't done this stuff before. Yeah, that's about it. Hope this helps. Thanks for watching.